Did you guys have a good weekend? That good, huh? It was definitely not where we left off, so it is lying. We did this one though, I think, right? I don't know. I can't remember if we got to this one yet. No? Yes? No? No, okay. All right, then we will do this one. Okay, so this needs to be zoomed out. All right. So a train is traveling along a straight level track at 26.8 meters per second. Suddenly, the engineer sees a truck stalled on the track 184 meters ahead. If the maximum possible braking acceleration is 1.52, can the train be stopped in time? Okay, so first things first, we need to list out what we have. Okay, at least that's what I think is the first thing to do. So what is this? 26.8 meters per second. That's your velocity. Which one? Initial velocity. Why? What's our final velocity going to be? 0. Why? Because we're stopping. Okay, so usually it's like it starts from rest to this, but this is flip-flops, right? We're starting something and we're stopping, so our final velocity is 0. What's 184 meters? That's our distance. And so far we're only in the x direction. Hopefully trains aren't traveling upward at this point. I think this is a train. Yeah, a train. So then what else do we have given to us? Acceleration. Are we given time? No. Could we find time and then solve for another equation? Yes, but really we don't have to. We could solve for what to see? Oh, it's giving you the strategy right there. It's telling you could find the distance that could be traveled with that acceleration. And if the distance that's traveled is more than what it gives you, then it can't be stopped. But if it's less than, then it could be stopped. So the point being is that when you go to do these problems, there could be more than one way to do it. Okay, so with the info that we have though right now, do we have an equation that has final and initial velocity, acceleration, no time? The fifth one, right? Which looks like this: b squared equals b naught squared plus 2a delta x. I know we have x, but we're actually going to try to solve for x and see if it's either greater than or less than the x that's given. Okay? So if we're solving for x, we've got to rearrange it. So x equals what? Final minus initial over 2a. And I'll tell you right now, people miss that squared on the velocities all the time. So try to keep that in mind whenever you're using this equation. All right, so what is our final velocity if we're stopping? 0. Do you really, I mean, you don't have to put it, but, I mean, you don't have to square it, but because it's just still gonna be 0. What's our initial velocity that we got? 26.8 squared over 2 times 1.52. Now, is it really 1.52? Like positive 1.52? We didn't really discuss this, but we should have. what's happening to the train? Slowing down. So what should the sign of the acceleration be? Negative, and we didn't put that. But does it make sense that it is? It's not going to give you negative one. It's not going to give you a negative acceleration in the problem, unfortunately. It's going to tell you that it's slowing down, and you're going to have to know to put it. Okay, so if you put that into your calculator, hopefully you get 236 because that's what I have written. You got that? Okay. So what was the distance that it said that the truck was stalled at? 184. With that deceleration, it goes 236. So what's going to happen? Bad, right? So that's where it's saying it cannot be stopped in time. Okay. Have you guys started on some of these kinematics ones in chapter 2? Bad? Getting better, at least? Okay, that's good. Since we've started talking about it a little bit more. Well, if you've done any with free fall, it's probably been a little bit harder because we haven't gotten to this part yet. So this is what our lab will be tomorrow. So we do have lab tomorrow, not a test tomorrow. Thank goodness, right? Okay. So free fall is when an object is it's exactly what it sounds like. It's falling through the air, right? So what is it experiencing if that's the case? Gravity. So that is a constant because I showed you with the book and the paper, right? Did it matter what the mass was? They all fell at the same rate. So just know that the acceleration for a free fall object is 9.8 meters per second squared. And if you go away from this class and you think, wow, I didn't learn anything, I hope you never think that. You'll always remember 9.8 meters per second squared. It'll be a bit of useless information that you have in your brain for hopefully forever. I hope I instill that into you, that constant.
Wait, is that gravity?
Yeah, that's gravity, it's acceleration. So I don't give that to you, okay? You just have to know 9.8 meters per second squared. So you throw a ball into the air with a speed of 15 meters per second. How high does the ball rise? Okay, so what is the only information that it gave us as far as numbers in this problem? Velocity. What kind of velocity? The initial velocity, 15 meters per second. All right, if you throw a ball up or down in the air, what is it experiencing? Gravity. And it's not going to tell you that. It's just going to say something like this. If you throw a ball, or if you think of another thing that would happen when we get into projectiles, if we shoot a bullet, what is immediately pulling on the bullet as soon as it's fired? Gravity. I mean, so all different situations, but if it's in a free fall, gravity is affecting it. So even though it didn't say it, we need to write it. A equals G equals 9.8 meters per second squared. Okay, and this is actually wanting us to find what? It says how high. So what is that? That's a distance. What is the symbol that we've been using for distance so far? X. But if we're talking about how high something is going, we need to change that to what? Y. Now we are no longer in the horizontal direction, we are in the vertical direction. So now we are looking for Y. Do you think that it changes the kinematics equations at all? No, instead of X, we replace it with y. Okay, there's nothing else changing besides that. Okay, so let's see. You could technically, I like the fact that it doesn't give time should tell you to use which equation first off. I'm going to do this one first. Go look at your kinematics equations really quick. And this is saying you throw a ball into the air with a speed of 15. How high does the ball rise? So what are you going to assume at the very highest point? What is the velocity at that point? 0. For a split moment, if you throw something in the air, then it is like has a 0 velocity for a moment. Okay, so its final velocity is 0. Okay, so we're gonna do this one first. So go through your kinematics equations. Which one solves for position, has velocity, and has acceleration in it? Anybody? 5? Okay, so 5 is this again, right? But that doesn't solve for position. It solves for final velocity. But can you rearrange it so that it solves for position? Yeah, this is the hardest thing with physics, is trying to figure out which equation to use. So that's why list out what you have, then look at your equations to see which variable you could find. So we're solving for y. Y equals v squared minus v naught squared over 2a. Same equation that we just used. What is the final velocity at the top of the height there? 0 squared again, minus the initial velocity that we were given, which was 15. But we got to make sure and do what? Square it or it'll all fall apart. 2 times, okay, what is the acceleration? Even though it did not give it to you in the problem. 9.8, is it positive 9.8? Gravity's always pulling down, always pulling down, right? If gravity starts to pull up, then that'd be weird.
Does that mean it's always negative?
It's always negative. Okay, so what do you get? 11.5-ish meters. Can I see your calculator really quick? Does anybody have a calculator, a Casio calculator?
Yeah.
Does yours have this exponent button at the bottom then?
No.
No? Okay, then it doesn't apply. If you were having to do like times 10 and you had a calculator that had this would be your times 10 button. That's the only reason I wanted to point that out. Okay, so this other way. All right, so let's find the time of the flight. This is a two-stepper to find the same thing that we just found. So what do we have? We have initial velocity. We have final velocity. What else do we have? We have acceleration, right? So look at your kinematics equations again. What do we have that has velocity and time and acceleration in it? So 2, right? It looks like this. Can we solve for time using that information? Yes. Time equals final minus initial over A. What's our final? 0. Our initial, 15. Our acceleration, negative 9.8. What do you get? 1.53. If you don't put the negative 9.8, what would you have got? Negative time. Can you have negative time? No. So why would you want to solve for time to find position? Well, do we have another equation that uses time in order to find position? Yes, we have this one, right? Y equals y naught plus BOT plus 1/2 AT squared. What's y naught if it doesn't say? 0. Now, with that being said, it might start giving you an initial position. It might say it's starting at 2 meters above the ground or something. Have you gotten to any problems that have done that yet? No? Well, if you do, that isn't 0. What's our initial velocity? 15. What's our time that we just solved for? 1.53 plus 1/2 times what's our acceleration that we're using? Negative 9.8 times 1.53 seconds squared. I really hope that we end up with 11.5 again. We will. .47 is what I got. I plugged them in. So 11.5 meters. Obviously, the alternate method was the fastest, right? But you can definitely solve for time and then solve for position. Okay. Next. Okay, so this example is apparently number 57 in the back of your book. So a penny is dropped from the observation deck of the Empire State Building, which is 369 meters above the ground. So what is that?
Murder.
It's meters. What is it
I
though?
was saying murder.
Oh, it's murder
It would be
of the
murder
penny.
to throw a penny.
I mean,
far.
if I was below and got hit by that penny, I would be ticked. That would hurt.
Dead.
Maybe if it hit the right spot, possibly. That would hurt. Yes, murder. I like that. So, what is it though? What is that number, that 369 meters? It's distance. Is it
What?
initial distance or final distance?
Initial.
Yep, initial, 369 meters. What's your final distance?
0.
I typically would say that you need to make the ground 0. If you would have made the initial position 0, like if you would have made the top of the Empire State Building 0, then the final position would have been negative 369 because it would have fallen down in a negative distance, okay? So just hopefully that makes sense. We're actually looking for, it says what's the velocity? Yeah, what was the velocity that it would strike the ground if the air resistance was neglected? So we're trying to find final velocity. What are we going to assume the initial velocity is since we're just dropping it? Would it affect it if you would have thrown it down. Yes. Yeah, absolutely. Doesn't give you any other information, but we have other information. What is it?
Acceleration negative 9.8.
Yep. Notice it never said anything about acceleration in there, but if something is dropped, thrown, you got to remember gravity, okay? So, what equation should we use? 5.
I think I'm having a hard time figuring out which equation to use every time.
Yep, it's definitely a process.
It's almost always like between 4 and 5.
4 and 5 are used the most, for
Okay.
sure. 4 and 5 are definitely used the most. But you have to have the first 3 to get 4 and 5. That's why we went through the derivation, or like the deriving of the other two. Because thank goodness somebody did that, because it does make it easier. We're solving for final velocity, but final velocity is squared. So what do we need to do to get it by itself? Square root it. So all of this is like to the square root. What is initial velocity? 0? Do we need to put it? No. So you've got the square root of 2 times negative 9.8 times the change of position. This is why there is, and this is technically change of position, because what was our final velocity? 0 minus our initial velocity, which is really important because what's that going to do? 0 minus 340 or 369 is going to give you a negative. A negative times a negative is going to give you a positive. If you have a negative under the radical, it's going to give you an error. Or, oh yeah. So, well, yeah. Not going to get there and go there. Don't get me started. So then, if that is the case where you've forgotten to do that or whatever, you might check, your signs. So what do you get? 85, I think. Okay. 85 meters per second. Okay, think about that. You guys know what a meter stick looks like. 85 of those in a second. Ooh, that might kill you. You're right. I would not want to be the person that got hit by it. I mean, it is just a penny, but still, that would hurt. All right. Has anybody ever been to the Empire State Building? I went to New York and we didn't go to the Empire State Building. And now I'm like, why did we not go up to the top? That was weird. We did every other thing.
Ted Mosby would be disappointed.
Do what now?
Ted Mosby would be disappointed.
I know. I have to go back now. We had to fit a lot in a little bit of time. All right. How long does it take for the penny to strike the ground? So now that you have the final velocity, you could do this. You could do number 2 if you wanted. It does it in the, it actually shows it doing number 4.
I was going to say, why would you choose 2 over 4? Is it just faster? Easier?
Well, this is 2. This is 4, right? To me, the second one would be easier because you're just doing it like that, but they show it doing this way, which ends up having a square on the T, so you end up having to do the square root, which is fine, but let's try it both ways. So what's our final velocity? What did we just find? 85? And yes, it hits the ground, but when it says something like that, it means right before it hits the ground. Okay, so 85 meters per second minus the initial velocity, they dropped it, so this one really is 0. And then they get it to be, our acceleration is,
Well, your time would be negative.
yeah, your time's negative in this one. But it actually does come out to be the same either way. So this is 9.8 or negative 9.8. But technically, I'll show you how this fixes itself. We solved it for 85 meters per second. Which way was it going? It was going down. So technically, what is this? Negative 85. So it is very possible that you would have solved for this and you would have put this in and it might have said no, because it would have technically been negative 85 meters per second. I'm not sure how picky it is on that, but so yeah, this is 8.7-ish seconds. If we would have done it this way, what would this value have been? 0. What would y not have been? 369. What would VO have been? 0. So all of that would have gone away. Plus 1/2 times negative 9.8 times t squared. This is a good reminder how to rearrange our equations, okay? If that's something that is troublesome for you, hopefully this is good practice. What do we need to do first? I would get this part over first. So how do you get that over? So it's 0 meters minus 369 meters equals 1/2 times negative 9.8 t squared. So you could go ahead and divide by 1/2 times negative 9.8. You could divide that over, or whenever there's a half, I tend to always do 2 times. If there was a third, what would you multiply it by? 3. Okay, so just since it's 1/2, it's multiplied by 2. So that gets rid of that. Divided by negative 9.8. So you have 2 times negative 369 divided by negative 9.8. So right now, if I just do this math right here, I have 75.3-ish equals t squared. So what do I have to do? Do the square root of that, which is 8.7-ish seconds again. What do you guys think? Okay, I have to do another example that it's not giving us on here, and I don't think that I gave you very much space, and I know we don't have very much time, but we have to do one like this before you guys get completely finished with chapter 2. So it looks like I picked number 62 in the back of the book. If you don't have the physical book, that's fine. But you have a way of getting to this. So I need to use a blank slide somewhere. Do I have one anywhere?
Is that at the back of the book or the back of the chapter?
The back of the chapter. Yeah, the back of the chapter. Did I say book? I meant chapter. All right, I'm just trying to find a blank space to get as much writing as possible. So you guys are gonna have to write this on the back page here or on another piece of paper. All right, so number 62. and it's probably gonna have to be finished on Wednesday, but this says that a stone is launched straight up by a slingshot and its initial speed is 19.6. So its initial speed is 19.6 meters per second. And it's 1.5 meters above the ground. So what does that tell you? That it has initial position of 1.5 meters. So where I said that you might get into some of those situations, this is a good example of that. And at first, it wants us to find how far or how high above the ground does the stone rise. Okay,
Is that why final?
yeah, like why final? So this is wanting us to find how far, how high it gets. And then it doesn't give us something but that we should know in this one. What is it? Acceleration is negative 9.8, right? Okay. What is our final velocity? It didn't give us that either, but we should be able to assume that if it gets to the highest point, then what is our final velocity? 0. Okay, so we're gonna solve for y first. We have to know y before we can do this next part. So if you look through your equations, we have v squared equals v naught squared plus 2a delta y, right? We can find our y by doing, okay, I'm solving for final y, but this is change of y. So what does that mean really? Y final minus y naught, right? Do we have a y naught in this situation actually? Yeah, so we have to include that in it whenever we rearrange it. Okay, so let me erase this really quick, or a little tiny bit of it, just this. So this is like y minus y naught equals v squared minus v naught squared over 2a. But what do I have to do to this y naught to get y by itself? I got to add it back over, right? Okay, so it's really like this. It's like y equals v squared minus v naught squared over 2a plus that initial position. So what is my final velocity that I said again? That it doesn't say, but we need to know that if it gets to the top height that it is 0. Minus my initial velocity, which was 19.6, divided by 2 times what's gravity, or acceleration, I mean, is gravity, negative 9.8 meters per second squared. And all of that plus 1.5 meters. What'd you guys get? 21.1, that's what I got, okay. 21.1 meters, okay. That was just part A. Part B is really the hardest part, but I don't have time to do it, so we'll do it on Wednesday. So I'll just like get you guys geared up for it. You know when you did the quadratic formula in algebra and you were like, I'm never gonna use this again, why am I learning this? Did you ever think that? Well, you're gonna use it again to find something, and it's actually relevant, I think, anyway. So, does anybody remember the quadratic formula? You do not have to have the quadratic formula memorized. However, by the time you get done, you'll probably have it memorized. Did you know did anybody have to learn it by a song? That's what some student sang it to me once, and I was like, I've never heard that ever in my life. No. Well, I mean, I have now because he sang it to me in front of the whole class. I was proud. Okay, thank you.
And then I had two very quick questions about this.
Yeah.
Okay, so in number 4, why can't we just use the final distance minus the initial? Like, why do we have to use all the distances? Because isn't displacement just,
Well,
or is it not the same?
yeah, because you have so many.
So I just didn't know what to do with it. I thought,
So this would be exactly what you would do if you had a stretch where it was all like going in the same kind of direction. But when you start, yeah, that's a good question. Because like if it was just falling down or if it was just being thrown up. But in the situation where it's like,
you're gonna take it.
yeah.
Okay. And my last thing.
Yeah, because I'm trying to think.
Was,
But no, you're right. Never mind.
Okay, and then, wouldn't it be 3 significant figures, or does this count as a 0? I was just confused. Maybe I don't know sig figs. I don't know.
No, you did it correctly. Oh, so I need to change that.
Okay.
So, what did I
I mean,
count
it
it as?
isn't-
Oh, okay. No, you did it. So that's why, I mean, it's definitely, so it's 11.5. Let me make myself a little note. Madeline. That'll help.
Okay.
Okay, there's that.
Right here.
And I'm just gonna trust you.
Oh, and I actually, okay, we're not leaving till Thursday now. I thought we'd leave Wednesday, but no, we're leaving at
Good.
4 in the morning on Thursday.
Well, ooh. But
Okay,
that's
it's
good
fine.
because we're gonna go through that,
Okay.
that one. You're gonna wanna be there for that.
Yeah.
I won't be here Wednesday, actually. I was gonna tell you that.
Fine.
Yeah, we have a soccer game, so.
Bummer. Okay, did I mess up on
I
yours
also have
too?
a question. So I got the 0.2 like you were saying.
Oh, but you did
But
it twice.
I went when it was released, then the sound back up.
Okay, yeah, see, I just thought of that as we were going over it.
So I
Yeah,
was just wondering if I did that part.
yeah. Let's see, so you took 0.0, okay.
Is it
Yes,
added?
you did it right. Okay, so. See, I gotta fix 2 now. So it would be just minus 0.25. So 12. Technically 12.2 for Lindsay. Okay, well, I think you'll be fine on the quadratic formula.
Yeah.
I don't think you're gonna have any issues, but still a bummer. I think Kim's